The Lagrangian method has uses in all sorts of different areas of physics. I talked a little bit about soap films in an earlier video this week. In this case, we're going to be talking about straight lines, optics, and geodesics. Imagine I wanted to fly from Atlanta to Sydney, Australia. I can't take a straight line path in Euclidean space. That would involve me digging a hole through the center of the Earth. So given that I'm constrained to live on the surface of the Earth, what path is the shortest that connects me between Atlanta and Sydney? Here is a flight going from Atlanta to Sydney, and this flight path is what's called a great circle, or a circle that passes through antipodal points or opposite points on the surface of a sphere. So it's the largest circle you could possibly have on a sphere. So this isn't a straight line in Euclidean space, but this is a straight line on the surface of a sphere. Imagine here I want to go hiking, and I spent the night backpacking out here, and my car is down here. So what is the shortest path between these 2 points? This is the straight line path, but depending on how tall the mountains are, a path that goes like this might actually take less distance. So the path that I want to travel is the path that's going to get me there as few steps as possible. So what does this have to do with optics? Imagine it's a beautiful spring day, and we're sitting by the side of the lake. The sun is shining, and we want to know what happens when a photon leaves the sun and goes into the lake. A photon comes into the air-water interface at angle alpha, but leaves it at angle beta. Air and water have two different indices of refraction. What Snell's law tells us is that the index of refraction of air times the incident angle of the light in air is equal to the index of refraction of water times the angle it leaves the interface. Fermat's principle, also called the principle of least time, says that the path taken by a ray between 2 points is the path that can be traversed in the least time. This is a little bit like our question about geodesics. What is the shortest distance between two paths? But in this case, this is the shortest time taken by a ray of light. Imagine I have this setup here, where I have linearly decreasing indices of refraction here, and they're all separated by some delta x. If I were to send a light ray into this medium, it would follow this trajectory here. So if you were to do this calculation using Fermat's principle of least time, it turns out that this is exactly the same as the brachistochrome problem. If you imagine you have a ball here and it's falling under gravity down here, and it is constrained to fall along some curved path like an inclined plane, you want to figure out the shape of the path that minimizes the time it takes to get from the top to the bottom. This path is called the brachistochrone. Fermat's principle extends well beyond the idea of ray optics. It extends to objects at the cosmologic scale as well. Einstein's theory of general relativity says that massive objects distort space and time. And yet Fermat's principle holds here as well. Photons have to follow geodesics in this space-time. They have to travel along the quickest path to get between point A and point B. This is an interactive simulation by my collaborator, Steve Treadle. In this rendering, what happens is that every pixel in this frame has a photon being sent out into the gravitational field caused by this black hole in the center here. As light rays go out into the space, they're being bent by the curvature of the space around this black hole. When a photon hits an object in the scene, we render it. But sometimes photons don't hit anything at all, like here, inside this event horizon of the black hole. These are places where light can never escape the gravitational pull of the black hole. We also have an Earth-Moon system orbiting the black hole. This is to help us visualize what's going on. As the Earth and Moon pass in front of the black hole, everything appears normal. But when they pass behind it, we see something really interesting. What we see is that the Earth and the Moon split up into these concentric spheres around the event horizon. So what's going on in those rings? This is another simulation by Steve Treadle. What this is an accretion disk surrounding the black hole. An accretion disk is similar to what happened in the birth of our solar system. You have a massive object that's surrounded by a cloud of dust and gas. But because it's spinning, this cloud forms a disk. Here we're looking at an accretion disk around the equator of a black hole, and the camera is moving up and down towards the north and south poles. What we can see is at the top of the accretion disk here, which would normally be occluded by the black hole, it stretches out into this upper ring here. And at the bottom of the accretion disk, we see this ring that's bent around the bottom of our screen here. So this is exactly what happened to the Earth and the Moon as they passed behind the black hole on the previous slide. This is a way of seeing behind a massive object. This phenomenon is known as gravitational lensing, or the way in which photonic images are distorted in the neighborhood of a strong gravitational field. Cosmologists use this to study very distant objects that may be occluded by massive galaxies. The strong gravitational field spreads out the images of the objects behind the black holes. This enables cosmologists to see two, as in here, or even more images of an object. If the light takes longer to reach the Earth from one image of this object compared with another image of the same object, then cosmologists can use this to study the dynamics of the system. They can see how an object changes over very different periods of time. Steve's shaders are available for you to play with. They should work with Chrome or Firefox browsers, and I'll link to them in the description below.